Hello, everybody, and welcome to my talk. My name is Patrick. I'm from Amazon Web Services. I'm a solution architect, and I welcome you to my talk on building highly scalable microservices with serverless. So, what are we going to talk about? Of course, microservices. And why serverless? Because how many of you have built or are still building or have the experience on building microservices? Let me see some hands. Come on. Okay, that's quite a few. And how many of you that raised their hands have encountered that microservices are not that simple, that there's a lot of complexity which you don't actually get at the beginning when you start building? So how many of you, only one hand, two hands, three hands? Okay, the number's rising. So good, my talk is justified. And so yeah, why serverless? Well, serverless is a way to mitigate these complexities. So why do we want to bother, if it's so complex, with microservices at all in the first place? See, when we think about businesses and companies, they work in an environment that is hugely complex. Even when you already have a monolith, there are a lot of integration scenarios within your company or within your business that you have to think about. Think about the connection to the ERP system, or think about the connections to this customer system, or to the order fulfillment system, or to actually any other external system. For example, if you want to buy a book on Amazon.com, when you think about it, it's pretty simple to buy this, but what happens underneath is pretty complex, right? You go to the website, it gets rendered with a lot of components. There's a component that has to update the stock. And then when you actually order it, the complexity just follows there. You order the book, it has to go to the fulfillment, the order fulfillment, the stock must be updated, the order has to be fulfilled in the fulfillment center itself. And when it leaves, it has to be kind of tracked, and you have to receive an email that your order's on the way. So you see, a simple process like buying a book can already encompass a lot of complexities. So enter microservices. But what exactly are microservices? And to explain what a microservice is, it makes sense to start with the monolith. So what is a monolith? And a quote by Martin Fowler says, or as Martin Fowler defined, a monolith is a single unit, a coupled single unit of a logical executable. And any change to this unit must follow that the whole thing needs to be redeployed. So in other words, when we break it down, a monolith is a tightly coupled code base, which is true in most cases, but you'll see that there are some exceptions to it. It is difficult to scale the thing because there's a lot of dependencies within these components. And therefore, we have also long development life cycles, because when we want to fix or work on a component, or when we want to update something, we have to redeploy the whole thing over and over again. We have limited technological flexibility within our monolith, because it is not easy to just change technology within the whole thing. In most cases, we will see a case where is the exception, but in most cases, it's hard to really have this technical flexibility. And it can be also considered as a single point of failure because of this highly coupled and interdependent web of coupling and connections. So the risk of a monolith are, on one hand, we have really long development life cycles. And therefore, we cannot really innovate on behalf of our customers. We cannot really produce new features every other minute, or every other, or not just features, but also fixes every other minute, because there's also this coupling and dependency. On the other hand, we have a financial risk, because we have to maintain this thing, right? We have dedicated engineering teams that have to be hands-on there and operate these things. Now, this might not be a financial risk per se, but only the thing that we have to spend engineering hours are opportunity risks. So the loss of opportunity that we could spend time otherwise for these engineers. And then there's, of course, the problem that when we have a single point of failure, we have the risk to lose customer trust, because when something happens, when the component fails, it's not a best experience for our customers. So we break it down into individual components and call it microservices. So, but But what exactly are microservices? And I like to quote Martin Fowler here again, and you see a pattern. I'm a Martin Fowler fan. In short, microservices are single small pieces of services that each run their own processes, where lightweight communication protocols and the services are built around business capabilities, which are independently deployable by automation. So in other words, when we have a monolith on one side, which does everything, we have microservices where each and every component, where each and every service does one thing and one thing only. And the benefits what we have from that is we have highly available systems and highly scalable systems. Because if one thing fails, we can ensure that the other parts of our microservice architecture are still working. We also have own databases and own data that is owned by these individual services because they have to be independent of each other. They have to work if other systems are down. So we have to have some sort of duplication of data there. Then we have independently deployable units. So we can have teams that are able to innovate and work faster, deploy faster, and release new features that have an actual business outcome. And of course, one critical step is the lightweight communication. So we cannot jeopardize our whole architecture if we use heavyweight communication with request response to see that something fails along the line. So that sounds really good, right? It sounds like we can have a lot from microservices. So let's refactor all our monoliths and make microservice architecture and everything will work fine. But as I want to quote Martin Fowler yet again, and I swear this is the last time for today, at least in my talk, if you do a big bang rewrite of everything all at once, you're guaranteed to have a big failure. So to illustrate this, I have a case study that I brought to you today. And this is, by the way, a real case study that was a project early in my career where microservices were the thing and every problem was solved by microservice architecture. It was the Gen AI of today, of then. So the case study is, it was a health system in an unspecified country where 80 plus million users were supposed to get a digital health record, which stored health documents. And the idea of it was to centralize all the business processes for health providers, insurance companies, hospitals, and so on to receive documents in one central health record. The challenges are there was integration into a lot of external systems. And of course, because it's a sensitive topic like health, you need to have security, data protection, highly available systems, and scalability. So how can serverless microservices help here? But let's start with the beginning, how we, in the project, we built this thing. And yes, this is the real architecture. It is simplified, but this is actually the component of it or a snapshot of it. So what we had here was we had a user profile service, we had a contract service that had to deal with all the contracts with the patients or with the insurees. And you know, everything has to go through a contract, so you have to sign a contract for everything. You cannot just use things. And when you use things, you have to consent to it. So you have to do a consent to actually sign the contract. Then you have the data exchange service, where we had the thing that all the documents that we wanted to exchange had to be routed through this data exchange service. And when you need to exchange data, you of course need a consent to it. So there was a dependency already. And then, of course, the document service, because when you sign a contract, you need a document to sign the contract. And the document service has to know whether you gave consent to it. So there's a lot of dependency. So let's see how this really mapped out in the real world. So when the user signed up for the first time, they went to the user profile service, which was kind of like the gateway, the API gateway, so to say, to this whole thing. And then you wanted to create a contract. But first, you needed to give the consent to actually do this. So to finalize the contract, the consent service needed to be consulted, and the document service, in order to send the document to the contract service, needed to check if the consent is there to actually do this. So when the contract then was, the consent was given, the contract was stored in the contract service, and then the user profile service could trigger the data exchange. But Of course, in the unspecified country, this is not just possible, so you need to give a consent to actually do this. So the data exchange service needed to actually check for the consent. And now this looks ugly, but it got worse, because every component, every microservice here had yet another component that was shared by all other components, namely the back-end common utility, a shared library of common enums, of common methods that was shared through all the service. And now you see two fallacies here, two problems in microservice architecture, or at least three. First, you see a very, very ugly dependency graph and interconnected coupling. You see a shared library, which makes all the components dependent on the backend common. So if you want to change something in the backend common, you cannot just release it to one service. You have to release all the services and retrigger the build again, at least in Java. And you broke each and every feature into its own microservice, which may not make sense. So in the difference of a large deployable unit and a single code base, this is not a monolith. But because we have highly dependent, highly coupling within each system and highly dependent systems, we have a distributed monolith. Yes, you could exchange the technology, but you still would have the dependency. So we just built a distributed monolith and called it microservice architecture. So, okay, what do we need to refactor this, or what do we need to consider if we really want to build microservices? For one, we need to encapsulate our services into business domains. We need to understand what the business case is actually happening and create boundaries or bounded context around our microservices. Domain-driven design could be a tool how you can identify those business domains. The other thing is we have to think about the communication, inter and intra communication. So we need to think, how could the components communicate with each other, and how do they communicate within each other? Because again, if we deploy microservices, it may have different components, it may have different libraries that rely on communication within each other. So we need to think also about that. And then of data and state. What is actually needed within our microservice? Which data are we relying on? What is the state we need to be aware of? And the other thing that is always neglected in distributed systems is physics and latency, namely. So when we started to build microservices or distributed systems, or our monolith, our distributed monolith, we assumed that latency is always zero, but that is not true. There is always some sort of latency within distributed systems, and that's not the only thing. We have to think about consistency. We have to think about data duplication. And what I like to also throw in here is the CAP theorem. So anybody aware of the CAP theorem? Okay, so the CAP theorem is consistency, availability, and partition tolerance. And you can only have two of these things in distributed systems. So you can have a consistent and available system, highly available system. You can have partition tolerance or consistency, or you can have availability and partition tolerance. And you need to think about what you actually want to achieve or what makes sense for your business. Okay, let's go on with refactoring our monolith. So let's identify business domains. How could we do this? Anybody aware of event storming? Anybody experienced with domain-driven design and event storming? I see shaking heads. The hands, we get less hands right now for the people that are streaming, so we have less hands. So when event storming is, this picture looks very chaotic, and event storming can be chaotic. So what we do is you invite people, domain experts, into your one workshop where you talk or model the business that you're into. So you have the CEO, the C-level, you have VPs, you have managers, and you have developers, because the artifact of the whole process is actual working code. And the good thing about event storming, which is a little bit exaggerated here, you go with post-its and design and model the business process where you can identify business domains. At the end of the talk, I'm going to have a link list where I'm going to also share the principles of event storming, and I highly encourage you to actually check this out because it can give a lot of value, independently of whether you do microservices or want to understand the business. So, microservices are challenging, and an example of that is Amazon.com. This is the dependency graph of microservices from 2008. And you can only imagine how this looks right now, because this is a couple of years ago, right? I don't know from which year this is, but this is the dependency graph of Netflix. And what you can see here is that you have a very good component that serves as kind of the gateway where each and every service or subsequent service is called and grabs stuff from other services. So you can see there's some dependency, some latency involved here as well. Some fundamentals of distributed systems which you have to consider when building microservices are, you need to think about coupling. And what you want to achieve with microservices is, or to build a highly available, highly reliable system, is to think about how coupled are these systems and how I can achieve loosely coupled systems, so to reduce the dependency between these components. The other thing is, how does my data flow and how do I control actually the data flow? So flowing packets or messages from A to B is one thing, but I have to think about how do I fetch these messages or how do these get there? Because message semantics matter. Do I need to first have first in, first out? What about duplicate data? Do I need to remove it? Do I have a mechanism for deduplication of the data? And the last but not least, what about errors? Errors happen. Technology fails all the time, each and every time. So this is a given. And when this happens, you have to think, how can I revert this? How can I live with the error? How can I reduce the duplication? How can I achieve consistency in things? So back to our case study, let's go through the communication flow within our system or within our microservice. So remember, the user called the microservice user profile service, which then in turn called the data exchange service. The data exchange service, of course, needed to call the consent service to check the consent. But now we have an error. The consent service is down. And what happens is that the whole process, the whole chain is down. The data exchange service goes down because it has a synchronous call. And then the user profile service was down. So the whole user flow was disturbed. And the question is, do I really need the synchronous flow here? Can I not just send the packet, send the request, and make the self asynchronously? And it's not just that. How do I communicate? How is the interaction model with these components? Is it pub or publication pub sub model, or is it point-to-point integration? What is the data and the control flow? Do I need polling? Do I need to specify a data format? How distributed are my systems? Are these systems or instances? What about failure, conversation rate, retries, idempotency? A lot of questions. Who is discouraged now of building microservices? Okay, not raised hands. Very good. So how can we mitigate this complexity? We have complex systems. Microservices are not easy. But there are ways we can make our life a little bit better. In order to reduce complexity, we could start with serverless. Another thing is, there are well-known integration patterns of distributed systems. So why do we need to reinvent the wheel when we can just use well-known patterns? And the other thing is, we need to think about automation. Let's automate everything we can in order to avoid the pain of managing some sort of crazy deployment flows. So one thing that we're not going to cover is the visibility, but which is also very crucial in distributed systems because you want to see how data flows, how communication flows from A to Z. So why serverless? The first thing when we think about serverless is that serverless is the abstraction of all the infrastructure. So we don't have to manage the infrastructure. We have no operational overhead to manage infrastructure. That is on us. That is on AWS. The other thing is, when we go to serverless, we have automated scaling with these services already out of the box. So this is one thing that we don't have to think about when we deploy services. The other thing is, we pay for use. So you don't have idle infrastructure that is just running. When you are super successful, and I hope so, that you really are, you're getting charged for that when you're super successful. When nothing happens, you're not getting charged for it. So this is also something that is kind of predictive and kind of fair. And the other thing, last but not least, is serverless is highly available and secure out of the box. And I mean, when you deploy code, you have to think about the code that you're actually writing, if that is secure, if it makes sense. But at the lower levels of infrastructure and of operating system level, hypervisor, you don't have to care about this anymore because this is on us. We make sure that these components are secure by design. Would I say serverless is the only way to go? Absolutely not. Serverless is a really great way to start, but when you see the problem, when you come to the point where you don't get any further with serverless, you can always iterate on other things. So there's the question, do I use serverless functions or do I use containers? And you can use containers and serverless, but you're not bound to use full-blown serverless if this doesn't make sense. You can go to containers, you can go to Kubernetes, you can go to ECS, this is our managed container service, or you can even go to virtual machines if it makes sense for your business and might improve cost efficiency or developer efficiency. Serverless can also make deployments easier. So anybody aware of these services? So who knows Terraform? Serverless application model, SAM? Amplify? CDK, or for short, Cloud Development Kit? Okay, only 3 hands. Wow, we need to make this more prominent. So CDK is actually what I'm going to focus now because it's really cool. When you have these things like, or services like serverless, Terraform, SAM, and Amplify, you specify infrastructure in a declarative configurational way. Whereas with CDK, you write infrastructure as actual code. So you can use your familiar language and write the code and specify your whole architecture, your whole infrastructure by using code. The great thing that gives us to write this as actual code is the level of abstractions we can use. For instance, this network load balance Fargate service, which is a serverless container service, by the way, is specified in just 4 lines of code, whereas in Terraform or in CloudFormation, you would need hundreds of lines of code to even specify this. The other thing that is a benefit of using code to define architecture is the tool support we can use, like inline documentation, linting, or autocompletion. For those of you who have now piqued the interest of trying out CDK, and I highly encourage you to do so because it's really awesome, it's available in TypeScript, JavaScript, Python, Java, C#, and Go. So when we define infrastructure and we use infrastructure as code, we have the provisioning of infrastructure. Then we need to deploy our application to this infrastructure. We need to think about the composition of all this infrastructure, of how these elements actually talk to each other. And then we need to think about the configuration, production endpoints, log level, databases, and so on. So when we go to serverless automation, the infrastructure is on us, so you don't need to provision infrastructure anymore. And deploying an application is as easy as putting a zip file into an S3 bucket. So the only things that we need to think about is the composition and the configuration, which also makes the whole thing about distributed systems easier. So when it comes to composition, we have to think about the control flow, the data flow, asynchronous or synchronous communication. And when we think about configuration, the message formats that we want to apply. So with serverless automation, we don't have infrastructure as code, we have actual architecture as code, thanks to CDK. So some common deployment patterns of microservices or serverless microservice or general microservice, independent of serverless or not, are you can use either all-at-once deployments, where you deploy everything all at once, not the whole microservice, but service per service. You can have blue-green deployments, where you have a green path and a blue path, and you can switch the traffic from green to blue and switch back if you have an error, which is good for medium concurrency workloads. Or you can have canary deployments, where you deploy a canary and a portion of your traffic is routed to the canary, where you can increase the percentage from time to time and see whether it behaves as it should and route 100% of the traffic if successful, or just cut it off and go back to the old deployment, which is good for high concurrency workflows. So with all the great theory in mind, let's apply these integration patterns. And as I said before, I like to quote myself as well because it makes me mature. Don't reinvent the wheel. Use battle-tested and well-known integration patterns that make your life a lot easier. So how does it look like? So there are many ways how we can approach the integration scenario from component A through component B. We can use we can use file transfer, shared databases, connectors, messaging, APIs, streaming, orchestration, and choreography. And there are a lot of patterns. There are a lot of scenarios that we have here. For this talk, we're going to concentrate mainly on messaging and APIs and talk a little bit about choreography and orchestration. But the main star of the shows are APIs and messaging. So the first thing are synchronous and asynchronous communication, which we have already talked a lot about. What are the main differences? So first of all, when we talk about synchronous communication, we immediately expect a response from the receiver. Whereas in the asynchronous communication, we often have a fire and forget methodology where we send a packet or send a message and don't really expect an answer. We just have a fire forget or acknowledgement mechanism. So back to our case study and the real life case study, let's re-architect this into microservice. Let's decouple this monolith finally. So we applied domain-driven design magically, and we had a lot of workshops, and we reshaped all these microservices into real microservices, which are bounded by business domains they are actually in. And again, the disclaimer here, this is not the full-blown picture of each and every microservices, but in the sake of readability and cohesiveness, I focused on these. So what we have here is the health record service, which is the overall manager of everything, the entry point, the gateway, so to say, the orchestrator. And then we have a service for user onboarding management that does all the things regarding to onboarding users or onboarding, onboarding. Consent service, contracts, everything is now coupled within this in business domain. We have a service for patient history, which takes care of all the patient history, which is communicating with insurance providers, with hospitals, doctors, and so forth to get a cohesive patient history for the user. Then we have a data exchange service, which is solely for the exchange of ad hoc documents like x-rays, documents, letters. And of course, when we talk about insurances, there's also some bureaucracy involved because why not? So we have a service that is dedicated to all the bureaucratic insurance things like support calls, letters, text documents, and so forth. So how do we communicate within this whole microservice architecture? Do you use asynchronous or synchronous? And the answer is both, actually, because when you think of it as a user and I want to call the service, maybe I don't expect a response as a user per se, but the application or the front end, it would likely want to have a 200 status to know that the request was actually submitted successfully. So a good serverless service here to use is the Amazon API Gateway. And by the way, I'm of course focusing on AWS services, but you can look at other platforms and see what services make sense to you. In this case, I use the Amazon API Gateway because it's highly available. It has some functionality like throttling, and you can define routes to specific downstream services. Now, what goes on in the health record service? We make our call to the API Gateway, where subsequently we call the user processor. The user processor then stores all the data that is requested or important for the whole process. The insurance ID, the user ID, and basically everything that needs to be fulfilled by the whole request. From then on, we gonna need to notify all the other services. So how do we do this? The best way is, of course, to use asynchronous communication and therefore to use a message channel. When we have a message channel, we have asynchronous communication where we don't expect response. It's a pretty good way to decouple downstream services or services, the sender and the receiver, and the message intent could be a command, it could be a document, or it could be an event message. So there are two ways that we can use here. The one, we can use point-to-point integration, where we have a sender that receives packages into a queue, and we have concurrent consumers. So the thing that we have to note here is that not all the messages are read by all the consumers. They are competing against each other when it comes to reading the messages from the queue. A good way to use a queue is for buffering, where we want to give our downstream services time to process things, or for load balancing. Another way, which seems to be a very likely way how to integrate the notification thing is to use the pub/sub or the fan-out mechanism or integration pattern, where we have a topic that sends all the messages to all the consumers. But the problem is here, if one of those consumers is down, the messages might get lost. So how would this look like? Our user processor stored everything in the DynamoDB database, which is, by the way, a serverless database, and sends all the messages to a topic from Amazon SNS. Again, a serverless notification service. So serverless is more than just Lambda. It can be also managed services like SNS, SQS, and so forth. And you then distribute the messages to the subscribers. Now, I said if one component is down, we might experience that some messages might get lost in the whole process. So what can we do? Well, we can do both. We can combine the point-to-point integration and the fan-out integration and have a composite pattern, the topic queue chaining, where we have an SNS topic that's load balance or sends the message to all the receivers, and each and every receiver will have a queue where the message gets buffered and stored so that the actual receiver has the time to process it on its own pace and give the downstream services some time. So yes, of course, we're going to use that and use SQS to buffer these messages for the onboarding, for the microservices, which is great. Now we have a very decoupled microservice, everything is great, but we have a problem. So, of course, we have the user that sends the request, it is then stored, it's cached, it's then sent to all these microservices, but what then? We need to somehow aggregate all the responses for the so the actual user can have some value out of it. So how do we get these messages back? There's yet another pattern, and it's called the scatter-gather pattern. So we use, it is simplified here with pub/sub or the fan-out pattern, but it can also work with fan-out and queue chaining. But all the processors, all the responders process the whole thing and send their responses in a single queue where an aggregator can then compute, accumulate, search for the best response, does what is need to be done, and then store it to the processor. So in our case, what we did was, and I took out the queues here just for readability because it may be too much if not taken away. The microservices send their responses back to an SQS queue in the health record service. From there on, the aggregator computes the documents, it computes the contracts, it computes the patient history, and stores it into the database. Now, what we can do additionally here to give the whole system much more resilience and availability is we can now decouple the reader from the writer endpoint and introduce a reader service that offloads the writes from the reads. Now, what about security, you may ask? I said that when we talk about serverless services, security is already implemented, but there's something that you need to consider. So for the whole service, for the whole application, we need to have some sort of authentication, and the API gateway gives you the ability to introduce OIDC flows, so you can get a token, exchange it to authorize and authenticate. The other thing is we need to think about what happens inside the microservices, what happens inside our application. We don't want a topic that is too verbose and speaks to absolutely everything, or we don't want to have a processor that does absolutely everything, right? We want to restrict the permissions here. And one thing we can use is identity and access management, where we can define permission policies for each and every service so that it only talks to the right recipient. The other thing that we want to achieve is encryption. So KMS, Key Management Service, is a service where we can also encrypt all the messages, all the events in the services, in the databases, and achieve encryption at rest and in transit. So nice. We have a very good, perfect microservice architecture that does all the things that we asked for, right? And the answer is no, not always. There's always something that could work or not work. It's by no means the perfect architecture. Because I like to quote one other colleague from mine, Dirk Ferner, No architectural decision comes without trade-offs. There's some point where you have some pain somewhere. And your job as developers or architects is to identify the option that sucks the least. So when we think about all these trade-offs that came with this architecture, what about the consistency of the data? What about duplication? We haven't scratched on this. Services might deal with duplicate data. How do we deduplicate this? If we talk about multiple instances of these services and function as a service like lambdas, we might into an issue we have concurrent pollers that might process 2 messages from one queue. This can happen if you configure it not correctly. There are patterns like Saga pattern and other patterns that I cannot name right now that might help you here. So this is something to consider. The other thing is, we haven't talked about the event schemas. When we work with microservices, there is always some dependency to other microservices. So let's say we have 1 hour of our user profile service or the health record service. When the team that works on this service only changes the schema, it might have an impact on the other services, although they are perfectly decoupled by queues and topics and so on. So you also have to ensure somehow that there's a contract, that there's a well-defined schema that is considered or taken as the source of truth by all the other services and all the other teams. And the other thing that I have just scratched upon is you need to know what happens within your application. So you really need to have some sort of tracing and visibility into what is actually happening there. You need to monitor. You need to evaluate the logs, the metrics, and see where you can improve, where you can be more cost efficient. You can see in case of errors what actually is happening there. I didn't talk about dead letter queues. So when a queue message is not properly processed, you can send this into a dead letter queue. So this is another way how you can mitigate or be prepared for errors. So this is complex, right? We have a very, very complex system. Microservices are complex. They are not easy. And to sum it all up, a monolith might not be the worst idea to actually do something. So the question is, when do I use a monolith? When do I use microservices? And the question is a matter of business domain and business complexity. If my business is super complex and I have a lot of moving parts, microservices might be a good approach to solve these complexities. But when your business process is really simple, when it's basically a web server that you want to deploy, why the hell do you need even to think about microservice architecture? Why do you need to introduce more complexities when your business case or when your problem is actually solvable by one single unit? So, a lot of information, a lot about complexities, and I encourage you to continue your learning. So if you want to learn more, I have compiled a list of links that I will add to the link tree, but for now there are, I think, 4 or 5 links there. I encourage you to check it out, and there are also some great talks today, like I think Simon Brown is parallel, so you missed it, but I encourage you to check this out as well. We have Alex Koenig that is going to have a great talk about WebAssembly, which is also Kubernetes for microservice, so you might learn something from that. And we have Ian Cooper to talk about where microservices did wrong. So I encourage you to do that. And before I cut off and say thank you, I ask you one last thing, and this is give me feedback. So when you scan that, you can give me some feedback, how you like the talk, how you like the content, how you like me presenting. And it's quite simple. You can do this within, I think, 30 seconds if you're quick. I would be super thankful. And with that, I want to thank you for listening. And I'm here to listen to your questions. And you can always check me out or approach me through LinkedIn or email. So thanks a lot. And it has been a blast to steal your lunchtime.